Have you ever meticulously designed a high-frequency PCB, bought top-tier components, followed all the rules, only to find out during testing that your signals are completely distorted and the data is corrupted? When faced with this issue, many designers immediately try swapping out components or adding more decoupling capacitors. But the actual problem lies elsewhere. Your trace impedance is not controlled. In this video, I want to explain in the simplest way possible what controlled impedance is, why its absence will ruin your board. So, stick with me until the end of this video. When we talk about low frequency or basic digital signals, like a simple switch or an LED, the traces on the board act just like connecting wires. They have a tiny amount of resistance, but it doesn't affect the circuit's performance. But when the rise/fall times of the signal get fast, for instance, in USB 3.0, HDMI, or DDR RAM traces, that trace on the board is no longer just a simple wire. It turns into a transmission line. In this scenario, your signal behaves like a wave. If this wave encounters sudden changes in electrical characteristics along its path, a portion of its energy reflects back toward the source. This is called signal reflection, which causes noise, overshoot, and ultimately the corruption of your entire data. So, what is the solution? The solution is to keep the impedance of the trace constant throughout the entire path of the signal. We call this controlled impedance. Standard impedance values are typically 50 ohms for single-ended traces and around 90 to 100 ohms for differential pairs, like USB. But how do we achieve this 50 ohm value? The impedance of a trace depends on four main factors that are completely under your control. First, trace width. The wider you make the trace, the lower the impedance becomes. Second, copper thickness, meaning the actual thickness of your board's copper layer. Third, distance to the reference plane. How far is your trace from the underlying ground plane? Fourth, dielectric constant of the material. This depends on the board's core material. For example, whether you are using FR4 or Rogers. Before you even start routing, you need to precisely calculate the trace width based on your board's layer stack-up so that the resulting impedance comes out to exactly 50 ohms. Calculating these factors might seem complicated and intimidating at first glance. But don't worry at all. Our team is here to help, and we are offering a free consultation to help you calculate your board's impedance. Whether you are working on a 4-layer board or higher, we will show you exactly how to find the most accurate trace width using free tools or Altium itself. You can book your free consultation right now through the link in the description. If you found this video helpful, be sure to give it a like and let me know in the comments. Has your board ever failed due to impedance issues? Subscribe to the channel for more specialized PCB design videos. See you in the next video.